Hello and welcome to another CNCM lecture. My name is Dr. Chorla and we're going to cover the topic generating functions again. This time it'll be a part 2 to my other lecture, which I made a few months ago, I believe in July. So let's get started here. Let me just get my pen. All right, so let's start off with partitions with generating functions. So to start off with, we have what are partitions? Of course, that's the first logical question to start off with. And we have that a partition of a positive integer n is the number of ways that n can be split into positive integers parts. So for example, a partition of 5 is 2 plus 2 plus 1. Two partitions that have the same parts but are in a different order are considered the same. So the partitions 2 plus 2 plus 1 and 1 plus 2 plus 2 are considered the same partition. So alright, so here are the partitions of the first 5 integers. As you can see, we have one partition for 1, 2 partitions for 2, 3 for 3, 5 for 4, 7 for 5. There actually won't be much of a pattern to this, so there's no clear-cut formula, but we're going to derive a generating function for this in the next slides. So deriving the generating function, we can think of partitions as picking a certain number of 1s, a certain number of 2s, and so on. More formally, we can state this as the following. N, which is the positive integer, is equal to C1 times 1 plus C2 times 2 plus C3 times 3, so on until Cn times n for non-negative integer coefficients. So there are, of course, restrictions to the above coefficients, such as C of n should be 1 or 0. Obviously, it can't be 2 because then the right side would be greater than the left side, but I just listed this here to give you an idea of how we can represent partitions. So this handles the case where the order isn't considered distinct, as in there's no order to consider here since we were looking at the number of 1s, the number of 2s, the number of 3s, and so on. So let's move on. So let's think of that equation in terms of generating functions. So let's let n equal x to the n. If you've looked at part 1 of this lecture, you know that we usually look at generating functions, and if you want to find a corresponding value, like let's say um, there are n coin flips, how many ways are there to get 3 heads out of n coin flips? Then the coefficient of the term x to the n would be our answer. And that's mainly how we interpret generating functions, and that's how we set them up. So we can actually translate the above equation to the following equation. X to the n is equal to x to the c1 times 1 times x to the c2 times 2, and so on. It's basically the same equation, it's just that I put in terms of exponents. And it's true since we add exponents when we multiply variables. That's why there's a multiplication symbol here instead of an addition symbol. So if you actually multiply all this out, this actually gives you x to the n is equal to x to the c1 times 1 plus C2 times 2, and so on. It's the same equation, but in the exponent. So we can go a step further, since we know that x to the a times b is equal to x to the b to the a power. So we can write the equation as this. So we have x to the n, x to the 1 to the c1, times x to the 2 to the c2, and so on. So this equation shows that we can pick a multiple of each exponent from 1 to n. This gives us the following expression. So let me explain this a bit more. So in this group right here, this is the C1 times 1 group. We are picking a certain number of 1s. This corresponds to x to the 0, which means we're picking 0 1s. This corresponds to x to the first, which means we're picking 1 1. This corresponds to x squared, which means we're picking 2 1s, and so on. And we can do the same logic here for C2 times 2. Here we're picking 0 2s. Here we're picking 1 2. Here we are picking 2 2s, and so on infinitely. And the same thing for 3, and the same things on and onwards. So, to see why this generating function works, I've just explained that. We can see that for each group, the first group corresponds to 1 times C1, and so on. And so we can actually simplify this a little bit more. Using the infinite geometric series formula, we can express the generating function as 1 over 1 minus x times 1 over 1 minus x squared times 1 over 1 minus x cubed, and so on. So this actually gives us the generating function for partitions, and that is this right here. if you don't know what this notation means, it's just product notation from k equals 1 to infinity. So k goes from 1 to infinity, which means it's just 1 over 1 minus x, 1 over 1 minus x squared, and so on infinitely. That's just what that notation means. And so, oops, let me clear that up, sorry. I wrote x squared there accidentally. Uh, oopsie. Okay, there we go. Minus x. And yeah, this will just go on for 1 over 1 minus x, 1 over 1 minus x squared, 1 over 1 minus x cubed, so on infinitely. So that's what this notation means right here. Don't be intimidated by it. So yeah, this is the generating function for partitions, where the number of partitions for the positive integer n corresponds to the coefficient of x to the n in the expansion. That's how we interpret generating functions. And so if you were to actually expand this out, if you go back a couple of slides here, we could actually write this, like, if you were to expand out the first few terms, you'd get 1 plus, so it would be 1x, let me erase that mistake. So we would actually get like something like 1x to the 1 plus 2x squared plus 3x cubed plus 5x to the 4th plus 7x to the 5th, and so on. And as you can see, for finding the number of partitions, we can look at the number here, 5. 5 has 7 partitions. That's the coefficient. So that's how we interpret it. So we can also do manipulations with generating functions, and I'll explain what that means more. So we looked at this logic for generating functions, and we can actually get the generating function for partitions with odd parts. And that means that we can use the same logic, except let's look at that example here, n equals c1 times 1. However, in our original example, we had c2 times 2. However, 2 is an even number, and we don't want even parts. So we actually don't want this. We only want odd parts. And so we can change our equation from earlier into this, c1 times 1 plus c3 times 3 plus c5 times 5, only the odd parts. And this notation is back again. This just means that 1 over 1 minus, this is 1 over 1 minus x times 1 over 1 minus x cubed, and so on for all the odd numbers. This only counts partitions with odd parts, since we cannot pick any even parts. So the next generating function is the generating function for partitions with distinct parts. This means that we can only pick one of each part maximum. We can either pick that part or not pick that part. And that's how this function works here, this generating function. So what we have 1 plus x squared, and so on. Since we know the parts have to be distinct, we can only pick each part once, or we can not pick it at all. And that's what is happening here. This corresponds to picking the part, which is x to the 1. So picking the part that is 1, or we don't pick it at all, which is this one. And same thing for 2. We either pick the part 2, or we don't pick it, and so on. So, the generating function for partitions with parts that can be at most m is this. Instead of the infinity symbol, we have an m over here, which just means that this goes from 1 minus 1 over x, 1 over 1 minus x, 1 over 1 minus x squared, and so on, until you get to 1 over 1 minus x to the m. We don't go on infinitely. Since parts can be at most m, we can't pick parts greater than m, so we have to stop there. All right, let's move on. So here's an example. So let's do a little problem here. Prove that the number of partitions of a positive integer n with the distinct parts is the same as the number of partitions with odd parts. So, the generating function for the number of partitions with the distinct parts is this one. Remember how we said we either pick that part or we don't pick that part. So that's the generating function. And the generating function for the numbers of partitions with odd parts is this one right here. We're only counting the odds. This gives us 1 over 1 minus x times 1 over 1 minus x cubed times 1 over 1 minus x to the 5th. And so we can prove that both of these functions are equal. These two functions over here. This is the one with distinct parts, and this is the one with odd parts. Actually, no, sorry. This is the one with distinct parts, and we can manipulate it as is. So by difference of squares, we know that difference of squares is like this: 1 minus x to the 2k is equal to 1 plus x to the k, 1 minus x to the k. And that's what we're doing here, except we're rearranging this. So we actually have 1 plus x to the k. We're dividing here by 1 minus x to the k. So you have 1 minus x to the 2k over 1 minus x to the k. And that's basically what's happening here. So we're just expressing each part here, each part of this function like that. And so what actually happens here is, as you can see on the top, you only have 1 minus x squared, 1 minus x to the fourth, 1 minus x to the sixth. They all correspond to even numbers. And the denominator corresponds to all numbers, which means that we can actually start canceling. The next term will be 1 minus x to the fourth here, so we can actually cancel and so on. This will only leave us with these stuff in, like, let me explain this, with odd things, like 1 minus x, 1 minus x cubed, there are odd exponents here. That will only leave us with odd exponents. As we can see here, in this explanation, the top consists only of factors in the form 1 minus x to the 2k, so ones with even exponents. All those factors will cancel out with the factors in the form of 1 minus x to the 2k in the denominator, leaving only the factors in the form of 1 minus x to the 2k minus 1, the odd ones. But since there's no factors with odd exponents in the top, we'll have all the ones with odd exponents in the bottom. And thus, this is what we're left with, and this is the generating function for partitions with odd parts. And this is equal to the generating function of parts with distinct partitions with distinct parts. So they're both equal. For an integer n, the number of partitions with odd parts will be equal to the number of partitions with distinct parts. Let's move on to our next section in this lecture, and that is power series. Uh, so the definition of a power series is as follows. A power series is an infinite sum in the form of the following. It's quite literally a series where you have increasing powers. So it's an infinite sum in the form of the following. We have coefficient a of n, and we have x minus c to the n. And for a power series, c is considered the center here. So let me just list out the first few terms for you. We have a to the 0 times x minus c to the 0, which is just 1, plus a to the 1 times x minus c to the 1, plus a to the a of 2 of x minus c squared, plus a of 3 of x minus c cubed, and so on. As you can see, as we go on with each term, the exponent on the x minus c term increases. So that brings us to a little bit of calculus. If you don't understand calculus yet, this is just setting up some intuition for some later topics we're going to cover in this lecture. You don't need to know this, but if you do learn calculus eventually, you will learn about these, and you should understand the intuition behind the topics that we'll be going over in the next section. So this is the Taylor series. It's an infinite sum in the form of the following. It's a special type of power series, and so it's f of x is equal to this infinite summation of the nth derivative over n factorial. That's the coefficient. That is a of n of x times x minus c to the n. And so this is equal to f of c plus the first derivative of f of c times x minus c plus the second derivative evaluated at c over 2 factorial times x minus c squared plus the third derivative of f evaluated at c over 3 factorial times x minus c cubed, and so on. I'll show you more about that. You'll understand this more later. I'll cover an example with it real quick afterwards. But you'll also go over the definition of a Maclaurin series. A Maclaurin series is basically uh, when the center is 0. So when c is equal to 0. So a Maclaurin series is just a Taylor series with center 0. It just means there's no c in there. So, sorry about that. Let me continue onwards. So the expansion of E. Some of you may have seen this thing right here. Let's just skip to this real quick. E expressed as a Maclaurin series. Some of you may have seen this expansion for E, where E is equal to 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, and so on. So this is actually Maclaurin series. And the intuition behind this is that the derivative of e to the x is always e to the x. And so in that case, if we let x equal 1 in the Maclaurin series of e, which is e is equal to, as I said, the derivative of e to the x is always e to the x. Uh, hold up, sorry. Yeah, so the derivative of e to the x is always equal to e to the x. When you evaluate the derivative of, since remember, Maclaurin series is a Taylor series with center 0, when you evaluate the nth derivative of e to the x at 0, that's e to the 0. It'll give you 1. It'll always give you 1. There's a derivative of e to the x, no matter what order derivative it is always going to be e to the x. So that's is equal to 1. So what happens here is if, so this is the Maclaurin series of e to the x. Let me just write it up here. N equals 0, infinity of 1 over n factorial x to the n. If you let x equal 1, that'll give us e, and that'll give us the infinite summation that's described here. Sorry, but that's described here. 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, and so on. So it's just a type of Maclaurin series. So that sets up our common generating functions that you should know. These are frequent common generating functions that may come up in competition math. So you should either learn how to derive them or memorize them. So in part 1 of this lecture, I covered this one extensively, 1 over 1 minus x to the n. It actually comes from the negative binomial theorem. And basically, the generating function for this is 1 over 1 minus x to the n is equal to the summation from k equals 0 to infinity of this n plus k minus 1 choose k times x to the k. So yeah, if you want to learn more about this particular generating function, I covered a lot in my first part of this lecture on generating functions, so you should check that out. E to the x is a Maclaurin series. We covered this in the last bit. As I told you, the derivative of e to the x is always e to the x. If you evaluate the derivative of e to the x at 0, it's 1. So yeah, that's just where this comes from. You have cosine of x as a Maclaurin series, and this also comes from taking derivatives of cosine of x, and that has a pattern to it, and that's where this uh, generating function comes from. As you can see, it's alternating, -1 to the n. It means it flips signs every term. And yeah, I can list out the first few terms for you. It'd be 1 over 2 factorial, not 1 over 2 factorial. It'd be 1 over 0 factorial, x to the 0, plus -1 over 2 factorial, x to the 2, plus 1 over 4 factorial, x to the 4, and so on. And that just comes from the Maclaurin series definition of cosine of x. Similarly, there's a one for sine of x. It's the same. The derivatives go in a pattern, and I can list out the first few terms for this one as well. The first term would be 1 over 1 factorial x is 0, 1 over 3 factorial x is -1 over 3 factorial. Hold up. Be -1 over plus -1 over 3 factorial plus 1 over 5 factorial x to the 4th, and so on. And the next one that I've covered up is ln of 1 plus x is a Maclaurin series. This also comes from the pattern of in the derivatives, and I can list out the first few terms of this one as well. It'd be 1 over 1 x to the 1 minus 1 over 2x squared plus 1 over 3x cubed, and so on. It alternates. And there is the binomial theorem expansion. Most of you may know this. 1 plus x to the n is equal to the summation of k equals 0, n choose k times x to the k. Most of you know this like this. If I put a y here, this would be y to the n minus k. But that's 1 now, so that just doesn't exist because it's 1 times something is something. So yeah, that's just a binomial expansion. of 1 plus x to the n. And here's the generating function for the Fibonacci numbers. This one, you should search up if you want to know how to derive it, you should search it up on Google. We won't be covering it in this lecture. So this is just the generating function for the Fibonacci numbers, this one right here. And the generating function for the Catalan numbers is something that frequently comes up, this one, 1 minus square root 1 minus 4x over 2x. So we won't be deriving that one here either. If you want to learn how to derive it, you should search it up on Google. And a combinatorial identity generating function, similar to the one used for the Catalan numbers. We'll actually be looking at this later in this lecture. 1 over root 1 minus 4x. There's actually a relation between these two, as you would imagine. They look very similar. So let's move on. So here is the derivatives and integrals of a power series. And when you're evaluating some of these summations, this is important to know, especially if you know calculus. And if you don't know calculus, you might not understand this. It's fine. But when you do learn calculus, you should definitely come back to this and see the intuition behind it. But here it is. So a power series, as we have shown earlier, is this where the power of an x minus c increases and their coefficients in terms of a of n. And so the integral of a power series is just integrating the function f of x. And so what happens is we integrate each individual term because we can distribute the integral, and we get, there should actually be a plus c here. Don't forget your plus c. C plus a to the 0, x minus c plus a 1 over 2, x minus c squared plus a 2 over 3, x minus c squared. That should be cubed. Sorry about that. Yeah. So this is just integrating each term, as in this comes from the fact that the integral of x to the n is 1 over n plus 1 x to the n plus 1. So if you see a common power series, but it has this fraction type of it, like a variable in the denominator, you should maybe consider seeing if it's an integral of a common power series. Similarly, there's also a derivative of a power series. Once again, you can also distribute the derivative to each term. So you get a1 plus 2a2 x minus c plus 3a3 x minus c squared. This just comes from the power rule, where d over the derivative I can't speak today. The derivative respect to x of x to the n is equal to n x to the n minus 1. And that just comes from the power rule of derivatives. As you can see, there's no a of 0 term. Since that's a constant, the derivative of a constant is 0. And as you can see, that gives you a variable in the numerator. And so if you see a variable in the numerator of a common power series generating function, you should consider seeing if it's the derivative of that common power series. So let's cover a quick example with that. So we're going back to those two generating functions that I said could be related. So given that the formula for the nth Catalan number is c sub n equal to 1 over n plus 1 2n choose n, and we're given this summation over here, as you can remember, summation from n equals 0 to infinity of 2n choose n x to the n is equal to 1 over square root 1 minus 4x. Find a closed form for the generating function of the Catalan numbers. So our goal is to find a closed form for the following. Catalan numbers right here, which we can sub in with 1 over n plus 1, 2n choose n x to the n. And there is that variable in the denominator. That might mean that this could be an integral that could be taken of this power series. And so note that the integral of the given summation being this one right here, is this summation. As you can see, the power on the x to the n increases. It's actually n plus 1. And we have the 1 over n plus 1 term. And we can't forget our plus c. This should actually be in parentheses. This plus c is separate. It's a constant. And so with that given fact, we have the integral of the given summation, which we know that value was also given to us. So let's take the integral of both sides. And we have this expression that we found in the last slide. And then this is the integral of 1 over square root 1 minus 4x. It's negative square root 1 minus 4x over 2. Both of these should have plus c's, but I moved the plus c from here to here. This is just like if you let this be plus c1 and plus c2, this c is kind of like c is equal to c2 minus c1 type of thing. So I'm not forgetting the plus c there. And if you move on, we want to find the value of plus c. That's actually our final step. Subbing in x equals 0 for both sides, we have, since this starts off with n equals 0, the initial term is x to the 1, and it just keeps on going up. The powers just keep on going up. It's x to the 1, x to the 2, x to the 3. There's no constant terms. So if you sub in x equals 0 for both sides, for this side specifically, this will evaluate to 0. And we have here, this is going to be negative 1/2 because square root of 1 is 1. And then we have 0 is equal to negative 1 over 2 plus c. And this gives us that c is equal to 1/2. So the generating function on the left-hand side is actually shifted to the right by 1. Uh, that is, there's a difference. If you go back here, this has an x to the n. Oops. This has an x to the n plus 1. So we actually have to divide by x. So if we add plus 1/2 to here, we get 1 minus square root 1 minus 4x over 2. If you divide by x, we'll fix that shifted to the right by 1 problem, and that'll give us the closed form, which is 1 over square root 1 minus 4x over 2x. And if you go back a few slides, you can see right here, that is indeed what the expression is. So let's move on to the snake oil method. So the snake oil method made by Herbert Wilf is a powerful method that is used to solve some summations. The basis of the snake oil method is to create a series into a power series, and then create a double summation that will be easier to evaluate afterwards. So the basis of the snake oil method takes a summation here. Let's let the value of the summation be s. This will be in terms of n, and this is a series in terms of n and k, a of n and k. And so this is summation in terms of the bounds being of k. So let's convert it to a power. So what we do with the snake oil method is we convert it to a power series. So if you have n squared equal to 0 here, of s, x to the n, this just goes on to infinity. That's the definition of a power series. And so we actually have a double summation here because, as you know, s is equal to this bit over here. And so we can sub that in, and we get this part. The summation in regards to like the bounds here, n, k greater equal to 0 of this. But we can switch the order of the summation, and that will usually give an easier sum to evaluate. If we switch the order of the summation, that may give us an easier summation to evaluate. And if it's easier, we can just go ahead and straight up evaluate it. So this is best shown towards an example. I know this is a bit vague, but this is the basic structure of the snake oil method. Let's look at an example. Evaluate the summation from k equals 0 to infinity of k choose n minus k in terms of n. So our first step is to convert the summation into a power series. And as you remember, we bring in this n equals 0 to infinity summation and this x to the n. This will become our coefficient, this k choose n minus k, and this is x to the n is, the variable with the increasing exponent. That's the basis of a power series. So now we can reverse the order of the summations. That's the key part here. We put the k equals 0 to infinity on the outside, and we have n equals k to the 2k now on the inside because we switched the order of the summations. And we still have this bit over here, k choose n minus k of x to the n. We can see that the summation of n equals k to the 2k of k choose n minus k of x to the n is very close to a binomial expansion. In fact, if this term was an x to the n minus k term, instead of an x to the n term, it would actually be the expansion of 1 plus x to the k. If we can manipulate the summation to get, and actually I should probably show this more to you, if you take k to the n minus k and you start evaluating from n equals k onwards, you have k choose 0 plus k choose 1 all the way up to k choose k. And then the exponent will also decrease along with it. It's like a binomial expansion. And if you don't believe me, you can try it on your own. It is a binomial expansion. So what we're actually going to do is we're going to manipulate the summation. We're going to factor out an x to the k and put it right here. Since it's not terms in n, we can bring it out to this summation over here. And now we're left with k choose n minus k of x to the n minus k. This is the thing that we know is 1 plus x to the k. So we can actually simplify this. This becomes the summation from k equals 0 to infinity of x to the k, and this bit over here is 1 plus x to the k. And guess what we're left with now? A much easier sum to evaluate. Why? Because this is an infinite geometric series with initial term 1 and common ratio x times 1 plus x. Thus, the summation is equal to 1 over 1 minus x times 1 plus x, or 1 over 1 minus x squared. And the result of this manipulation actually gives us a generating function. The coefficient of x to the n in the expansion of the generating function will give us the result of the summation in terms of n. Well, if the n is fixed, it'll give us a constant, but the whole point is to get this in terms of n. So furthermore, this is actually the generating function for the Fibonacci numbers, but divided by x. That is, if we had x1 minus x squared, this would have the term f to the n, x to the n in its expansion. This is the generating function for the Fibonacci numbers. However, this particular one is divided by x. So if we divide by x here, let's have a minus 1 to this, which means that the x to the n term actually corresponds to f of n plus 1, which means that to put this summation in terms of n, it's the coefficient of x to the n term, which is f of n plus 1. This is the n plus 1th Fibonacci number. And so that is our answer to the summation. Thank you so much for watching. If you like this lecture, please consider liking the video and subscribing. Here's our Discord link. If you need any help with this topic in particular or any other math topics, please do join our Discord link. We have a huge community of people who are willing to help each other. We have a lot of people who are willing to help you if you have any problems in math. We have a math help channel. And so if you have any problems, just let us know. And the link to the handout that I used will be posted in the description. So I used a handout to make this lecture. And so many of these images here are from my handout that I just made for this lecture. And so I will be posting the link to that handout in the description below. That's all I have. Thank you for watching.